Hi everyone, I'm really glad to introduce our work called PF2ES, Parallel Feasible Parallel Frontier Entropy Search for Multi-Objective Bayesian Optimization. My name is Jixiang Qing from Ghent University. This is a joint work with Henry Mons, Tom Dana, and Ivo Kogat. We begin with a brief introduction of the multi-objective Bayesian optimization, and we introduce our PF2ES acquisition function, both of its sequential acquisition function formulation and its parallel acquisition function formulation. We demonstrate the effectiveness of our acquisition function through empirical multi-objective Bayesian optimizations problems, and we end up with conclusions. Multi-objective optimization considers maximizing a set of unknown constraints, unknown functions, represented by f1 up to F(M) here, and optionally it can also subject to a set of unknown constraints, which has been denoted by G1 up to G(C) here. Note that we use the constraint larger or equal to 0 to represent that the candidate X is feasible. Under the multi-objective optimization scenario, the optimality comparison of different candidate X has been determined by the dominance operator. A feasible candidate X is preferable to X prime in the sense that for any of the objective function, the X corresponding objective function value is larger or equal to X prime, and there should exist at least one objective function that f of x is strictly larger than f of x prime. And this is noted as f of x dominates f of x prime, or x is preferable to x prime. A feasible candidate input X is called Pareto optimal candidate if there do not exist any other feasible candidates in the design space that are able to dominate it. The set containing all the Pareto optimal candidates is called a Pareto set and is denoted as X of F. The goal of multi-objective Bayesian optimization is to quickly identify the feasible Pareto frontier, which has been constructed by a Pareto set. On the right-hand side, we have shown a discrete Pareto frontier on a B-objective optimization problem. And this is an illustration of the discrete Pareto frontier in case the number of the objective function equals 3. And this is an illustration of the Pareto frontier in case the number of the objectives is even larger. By making use of h of x representing the joint predictive distribution of the objectives and the optional constraint under the Gaussian process, and we can also make use of the p of f representing the predictive distribution of the Pareto frontier, the PF2ES acquisition function builds on having a mutual information between the Pareto frontier distribution and the joint distribution here. By subsequently plugging an additional term q here, we can write down this mutual information explicitly with respect to a KL divergence term. Since the KL divergence term simply resembles with one having a approximation distribution q to approximate the p, and we're aiming to having this approximation as accurate as possible, and we can simply ignore this KL divergence because of the non-negativity of the KL divergence, and subsequently we can have a information lower bound formulation of the mutual information. And the goal is to have basically a reasonable approximation Q, or the predictive distribution of the joint objective and constraint by observing the Pareto frontier realizations. So how should we have a reasonable approximation of Q here? Well, we simply utilize the approximation shown in the segment function. In short, this is a truncated distribution of the P, which has been normalized by a normalization constant Z of overlying of A here. So this approximation simply resembles that if we're having the realization of the Pareto frontier, the probability density shouldn't have any value larger than 0 that is in the non-dominated region. And we can subsequently write down the complement of the Z of overlying of A by making use of the Z of A, which resembles a probability of being in the non-dominated region. And with this notation, we can actually plug in this approximation in the information lower bound formulation to have a quite neat expression of the acquisition function, which we denoted as a PF2ES. Because Z of A, or this complement of the normalization constant, having a close relationship of the probability of improvement in the multi-objective optimization scenario, this really endorses our explainability of the PF2ES through the following remark. That said, the multi-objective probability of improvement acquisition function will having the same maximal acquisition function location as PF2ES under some certain scenarios. And of course, we have extended this connection in the constrained multi-objective optimization in the paper. So how should we calculate this complement of the normalization constant Z of A, or the probability of being in a non-dominated region? Well, this actually has been well established in the multi-objective probability of improvement research. That, to be more specifically, we need to first partition or approximate this intractable non-dominated region, or the yellow shaded area, to a set of rectangles here, which has been represented by tiled A1 to tiled A4. And this can also be done in higher output space, like in these cases we have in the objective number equals 3. And with all of these hypervolume based decompositions, the non-dominated region can be approximated by this set of rectangles or hypercubes. And this can also be done for the constrained multi-objective optimization scenario. So with all of these approximations, the probability of being in the non-dominated region can be approximated by the summation of probability of being each of these rectangles or hypercubes. And given that each of the assumption that each of the objective function and the constraint are statistically independent, we can calculate this probability of being in any rectangles in closed form. And subsequently plug in all of these in the acquisition function of the PF2ES, we can have an acquisition function formulation that can be practically calculatable through the following form. And final thing that we want to remark here is that our expectation with respect to the Pareto frontier F has been approximated by Monte Carlos that has been driven by multi-objective optimization on GB parametric approximations. So this PF2ES formulation can be easily extended to the batch scenario where we want to query a batch of points in a single iteration. So the acquisition formulation is quite similar, while the only difference is the normalization constant here. The tiled of AQ represented that at least one batch element is in the region of the tiled of A. Since this event involves complicated probability representations, which having an analytical formulation seems non-trivial, so we propose to make use of Monte Carlo approximation to approximate this normalization constant. And in reality, this has been powered by quasi-Monte Carlo and sample average approximation to hopefully to having a consistent gradient of this acquisition function as possible. As a proof of concept, we show here a one-dimensional with multi-objective optimization with batch query numbers equals to 2 per batch. So we are able to say that after 5 batch iterations, we are able to recommend Pareto frontier in a very accurate way. So how the PF2ES behaves in the multi-objective Bayesian optimization problem. So on the first row we show here is like the sequential acquisition function behavior, and the second row is like the batch acquisition function behavior, where the orange curves representing the behaves of the PF2ES. So under most of the scenario, we are seeing that PF2ES is quite competitive. And there is also one thing to remark is like the EHVI is actually a quite well-known golden standard acquisition function in the multi-objective Bayesian optimization. But here we say like for the ZDT1 and the ZDT2, actually they are performing quite less good as compared with PF2ES. This is simply explained because of the EHVI determines on the reference point a hyperparameter of the acquisition function that is sensitive to the scale of the objective functions. And here we are able to say that actually the PF2ES acquisition function does not really having such an issue because it mitigated the specification of the reference point. And we have also demonstrated the performance of the PF2ES for constraint multi-objective Bayesian optimization in the first row and this batch setting in the second row. And again, we are also able to say the competitive performance of the PF2ES. And also one thing to remark is because for the C2DTLZ2 benchmarking function that is part of frontier AISTATS joint, this also imposes some issues on the reference point setting for the EHVI related acquisition function, hence the degradation of the performance of this golden standard acquisition function. However, we are able to see actually that PF2ES does not deal in such a reference point. So basically its performance is very robust in terms of the shape of the paradox frontier. So the take-home message would be we introduce a new information theoretic acquisition function that has based on the lower bound of the mutual information. And it supports sequential and Monte Carlo based batch query for multi-objective Bayesian optimization with or without constraints. And the acquisition function has really a close relationship with the multi-objective probability of improvement, hence it does a nice explainability. And also the biggest empirical advantage of the PF2ES compared with, like, for instance, golden standard EHVI is that it's free of specifying a reference point, which we argue that it's actually unknown in most of the real life problems, and it will affect the performance of the multi-objective Bayesian optimization performance to a large extent, as we show in the empirical performance. Okay, that's all our presentation. Thank you for your listening, and our code is available through this GitHub link.